Hello everyone, my name is Tin Tran and today I will present our work on Dr. Lin's behalf. I am currently a postdoc in Dr. Herein group at the University at Buffalo. So today I am happy to present our work on Zwitterionic Hydrogel modified by gel-liquid interfacial polymerization with improved water over salt selectivity. This work is our collaboration with Dr. Herein at the University of Colorado Boulder. Osmotic pressure-driven membrane processes have attracted great interest for desalination and water purification recently. However, the conventional membrane design poses a significant challenge known as internal concentration polarization, or ICP. This phenomenon reduces the effectiveness of such membrane for this application. Many research has been done to resolve this issue. And support-free non-porous membrane has emerged as a new material platform for this application due to its insusceptibility to ICP. Here in this study, I will introduce our high-performance membrane consist of Zwitterionic hydrogel with a skin layer of highly cross-linked polyamide. I will then go over the structural characterization and our discussion about the membrane performance in forced osmosis application. After that, I will go over the major conclusion that we have from this study. A little bit of a background on forced osmosis. In this process, a membrane separated a draw solution with high osmotic pressure from a feed solution with low osmotic pressure. The water will then permeate from the feed side to the draw side, while the draw solute will permeate from the draw solution to the feed solution. The ideal driving force for this process is the difference in osmotic pressure between the feed and the draw solution. Current membrane design, as shown in this schematic here, would usually comprise of a thin selective layer with excellent water over salt separation property, and a porous support underneath to provide the needed mechanical strength. However, an interesting phenomenon developed in the porous support known as internal concentration polarization, or ICP. This reduces the effective osmosis pressure difference as shown here in this schematic. A previous study from our group had demonstrated that TFC membranes such as NF90 or SW30 membrane, or even state-of-the-art FO membrane aquaporin, would also has the TFC membrane configuration can exhibit more than 90% loss in driving force. This is indicated by the lower water permeance during FO as shown in this table here. In our previous study, we have demonstrated that non-porous membrane like polyethylene glycol hydrogel impregnated membrane can reduce water permeance loss during FO down to about 75%. In addition to that, symmetric non-porous membrane has been prepared and illustrated in the literature that this membrane configuration is also not susceptible to ICP. From our previous study, we also found that even though the PEG hydrogel impregnated membrane show minimal ICP effect, its reverse salt flux is high and hence lowering the water over salt selectivity. During this time, we conduct our own study and also found in the literature that the addition of SBMA or sulfobetaine methacrylate, a zwitterion in PEG hydrogel system can effectively increase the water over salt selectivity as shown in this figure on the right. Hence, for our first approach, we propose an impregnated membrane consist of Zwitterionic hydrogel instead of just PEG hydrogel. During the development of our Zwitterionic impregnated membrane, our collaborator at Boulder, Colorado successfully modified the surface of several gel systems with a polyamide skin via a process called gel-liquid interfacial polymerization, or GLIP. Inspired by their research, we take this approach to modify the surface of our impregnated membrane with a polyamide skin, which we hypothesized to further increase the water over salt selectivity. Here's the schematic for the gel liquid polymerization process. Simply put, a Impregnate membrane hydrogel will be dipped in an aqueous monomer solution containing piperazine and TAA as the catalyst. After 5 minutes, it will be taken out, remove the excess liquid on the surface, and then immersed in the TMC hexane solution for 5 minutes for the interfacial polymerization to take place. Here, unmodified Zwitterionic membrane will be denoted as Z, while polyamide modified membrane will be denoted as ZPA in later slide. With X is the PEGDA concentration in the pre-polymer solution, and Y is the piperazine concentration in the GLIP process. Additionally, membranes that do not contain SBMA will be denoted with the letter A in later slide. We utilize FTIR to confirm the conversion of acrylate or methacrylate groups. As shown in this figure, the three characteristic peaks of acrylate group do not present in the spectrum of the Z20PA2 membrane. We also use FTIR to verify the presence of the polyamide layer on the surface after modification. As shown in this figure, the four aromatic amide peak only present in the spectrum of the Z20PA2 membrane and not in the spectrum of the Z20 membrane. The surface and cross-section morphology of the membrane was also examined by scanning electron microscopy. The top row is the surface SEM images of the support, the Z20 and the Z20PA2 membrane, while the bottom row is the cross-sectional SEM images of the support and the Z20PA2 membrane. As you can see here, the support exhibits porous structure, while the Z20 membrane shows smooth surface because of the hydrogel. On the other hand, the Z20PA2 membrane shows wrinkle feature consistent with the PA layer of conventional nanofiltration membrane. The large feature you see on the surface of the Z20PA2 membrane was caused by residual aqueous droplet which were not completely removed before the immersion into the TMC solution during the GLIP process. The cross-section SEM image indicate that the porous supports were fully filled with the hydrogel due to the great compatibility between the solution and the support. I should note that we cannot distinguish the polyamide layer from the hydrogel, though we expected it to be less than 250 nanometer because of our short reaction time of only 5 minutes. The surface roughness and nanomechanical property was investigated via AFM by our collaborator at Boulder, Dr. Ding and Adrian. The formation of the polyamide skin increases the surface roughness from 4.9 to 215 nanometer. I would like to note that a larger skin size was chosen for the Z20PA2 membrane to illustrate a long-range surface wrinkle. This is consistent with our finding from SEM earlier. The surface modulus also increases from 118 megapascal to 1 gigapascal after the modification. These changes confirm the presence of the polyamide skin on our hydrogel membrane. Next, we investigated the effect of PEGDA content in the pre-polymer solution and the polyamide skin on pure water permeance and salt rejection of the membrane. As shown in this two figure, increasing the PEGDA content from 20 weight percent to 40 weight percent reduces the water permeance but increases the salt rejection due to the increasing cross-link density. On the other hand, the addition of the polyamide skin had negligible effect on water permeance but increases the salt rejection. For example, A30 and A30PA2 membrane exhibit similar water permeance around 0.12 LMH per bar, while the salt rejection increases from 49% for A30 to 84% for the A30PA2 membrane. Since the impregnated membrane with 30 weight percent polymer composition show a balance between water permeance and salt rejection, it was chosen for further FO study. This table demonstrates the FO performance of A30 membrane and A30 PA1.5 membrane. Both membranes show similar water permeance within the limit of uncertainty. However, the polyamide modified membrane exhibit significantly lower reverse salt flux, reducing from 325 to only about 16 grams per meter squared per hour. Thus, is increasing the water over salt flux selectivity by more than tenfold. A similar observation can also be seen for Zwitterionic hydrogel membrane. More importantly, the reverse salt flux of Z20 membrane is significantly less than that of A30 membrane, confirming that the addition of SBMA in the hydrogel will increase the water over salt selectivity. We also compare our membrane with commercial membrane, including FO membrane such as aquaporin and HTI membrane. Our membrane, even though exhibits similar water permeance, it has higher reverse salt flux during FO as compared to commercial membrane. However, our membrane are not susceptible to ICP, indicated by the low loss in water permeance, which is only around 10%, as compared to other membrane which are 60% and higher. We also investigated the anti-fouling property of our membrane by comparing our membrane performance with commercial HTI membrane during fouling. Using 1 gram per liter bovine serum albumin (BSA) solution as the feed, we can see here that even though both membrane has similar starting flux, our membrane over the period of 24 hours always exhibit higher water flux than commercial HTI membrane, suggesting that the Z20PA1.5 membrane is more resistant to fouling. So, in conclusion, I hopefully demonstrate that we successfully synthesize a new impregnated membrane configuration consists of Zwitterionic hydrogel with polyamide skin. This membrane can exhibit water over salt separation property for FO application comparable with state-of-the-art commercial membrane. The first major conclusion we can get from this is the addition of Zwitterion, such as SBMA in hydrogel, reduces the reverse salt flux while increasing the water over salt selectivity. The polyamide skin layer further reduces the reverse salt flux, hence increasing the water over salt selectivity more than tenfold. And lastly, our impregnated membrane, which are non-porous, are not susceptible to ICP and exhibit higher water flux during fouling compared to commercial FO membrane. With that, I would like to acknowledge my advisor, Dr. Herein Lin, for his guidance and support on this project. I also want to thank our collaborator at Boulder, Dr. Dane and Adrian, for their help on the AFM measurement. Thank you to my lab mate, and especially Ms. Xiaoyu Chen and Mr. Percy for their help on this project. Last but not least, I want to acknowledge the funding agency, NSF, and AIChE Material Engineering and Science Division for giving me the opportunity to present my work today. Thank you for listening.